Welcome everyone. In this video I'm going to show you how to control a DC motor using PID control, and the PID control in this case will be based on the position of the shaft of the motor, and what we will do is that we will read the position of the shaft based on the magnetic encoder attached to the main shaft, as you can see it here, and based on that we can generate a signal which will be a PWM signal and drive the motor in order to reach the desired position. And of course, if you know the position and you measure the time, you can do the same thing with the speed. But in this demonstration, I want to focus on the position because I have some further projects lined up which will need very precise position control. So then I wanted to sort of practice this and then demonstrate this thing to you. So how this thing works is that we have a motor, and in this case I'm using a geared motor because this is what I have. So this part is the main motor here, which is a DC motor, and on the back of it we have a sort of a magnetic disc, and this disc has 11 magnetic parts or different poles. So that means that when this disc does a full rotation around the shaft, it will generate 11 pulses in one of these two magnetic Hall sensors. So we have two Hall sensors here at different locations, so it means that we will have two output square waves or pulses with some delay in between the two pulses. And this is a very good thing because by checking the delay between the two pulses, more precisely checking which pulse comes first, we can determine the direction of the shaft, so whether it goes clockwise or counterclockwise. So we have the DC motor with this nice magnetic encoder, and on top of this part, we have 1 to 515 planetary gear box, which means that this shaft here has to do 515 turns in order to turn this shaft just once around, and I will show you how this works. And I programmed the Arduino in a way that when I increase the number of steps, or I increase the target position with the rotary encoder, one step will be equivalent of 515 turns on this shaft. So that's like more easy to set up like an integer number of position for us regarding the target position on the geared shaft. And another thing what we have to know about this encoder is that this specific encoder generates 11 pulses per shaft rotation, which means that if we have 11 pulses registered by the microcontroller, that means that this shaft rotated around once. But since we have this gear here, which requires 515 rotations in total to rotate this shaft around once, then we have to register 11 times 515 pulses with the microcontroller to actually have the one full rotation on the main shaft. So that's what we will keep in mind, but I will show you all the details, of course, when I show you the software. So we have an Arduino Nano here, and we occupy both of its interrupt pins, D2 and D3, with two encoders. One will be the magnetic encoder and one will be the rotary encoder. So the rotary encoder will be used to just set up a target position. You will see it how it's done. And also if I press the button, it has a button as well, then I will be able to start the motor and go to the next target position. And then we have an OLED display here. I will just show the target position and the current position of the shaft of the DC motor. And then this is the TB6612 two-channel PWM-based motor driver. So what we have here is just we feed 12 volts to this thing using this power supply. And then we have two channels, A and B. I'm using the A channel here. And the motor driver also has a PWM input and a standby input. So the standby enables or disables the H bridge inside the chip. And then obviously the PWM pin will determine the pulse width and therefore determine the power fed to the motor. And then there are two output pins, which are obviously the output pin which will feed the power to the DC motor. So what I'm planning to do here is just I will set up this system, plug in everything, and then I show you that with a certain target position we can go to a certain position on the shaft. And I will set up another camera just to have a better view on the display, because I think that with this camera up here we cannot see everything properly. So I just set up the camera and then we start this thing and we see how this works. So the camera is on. So now hopefully you can see the display in a better perspective. So I have to power up everything. So first of all I will power up the microcontroller, and then I give some power as well. So whenever I connect the external power supply, there is a small hiccup in the main shaft of the motor, so I just reset everything after everything is connected. And now you can see that we have 0 for both the target and both for the position. And the target is often called in PID terms as setpoint. So the target is the setpoint, which is now 0, and we will change that value. That will be the user-defined value. And then the position is the position basically provided by the encoder. So whenever the encoder generates a pulse, then the position will be also increased. And the core of the PID code on the microcontroller is that it tries to minimize the error, which is the difference between the target or set point and the position. So if it sees that the position is, let's say, 5000 and the target is 0, then the error is 5000. And what the software will try to do is that it will try to drive the motor until the difference between the target and the position will be 0. So now I will hold the motor a bit different way just to show the arrow better. And now I will also try to increase the target. And as I said, we need 11 times 515 pulses in order to get one full rotation on the geared shaft. So I will move there, and that will be 5665. So then if I press the button here, that should start the motor, and it should do one full turn in clockwise direction. So let's see what it does. So it's pretty much there, and you could see that the position was constantly updated, and then the motor was moving accordingly. And then we can go back to 0, obviously. So I do that. So now we expect the same kind of movement, but backwards. So we are there, and obviously we can go in the negative way. So I just set up the number to the -1 full turn on the main shaft. So let's see what it does. Then let's get back to 0. So as you can see, it works. So you can see that we can make this work relatively easily, and you will see it in the code in a few minutes that this is not a very difficult thing. Of course, there are some difficulties, but I will explain these difficulties when I show you the code. But you could see that with this very simple system, we could set up a very nice position-based control for the DC motor, and this can be very useful in many applications. And this is not the only thing where we can use this, but in this video I'm just showing you the position-based control, but of course you can just convert the whole code into speed-based control. So we can use the speed as some kind of target value or set point, and then the code will adjust itself and adjust the control value to get the proper speed on the shaft of the motor. So you could see that this demonstration works and the code works quite okay. So now I will go to my computer and I will show you how the code looks like on the Arduino. So let's go to my computer. So now we are at the Arduino code, and I will guide you through my code so you can see everything. But if you're not interested in the explanation, you just go straight to my website, link is in the description, and you will see this code. As you can see, it's commented everywhere where it is possible. So you maybe don't need this kind of explanation that I will do, but if you want, you can follow me. So in this part, I just have basically my old code, which I always use. So this is a copy paste from many of my projects where I use this specific OLED display. So you can just copy paste these codes. This will just set up the libraries and everything in order to work with the display. And whenever you want to call for the display, you just use the OLED instance. And basically, this is all. And now comes the maybe a bit more interesting things. We have the different pins which we need to define, and we have the different variables. So let's start with the motor encoder. So we have two pins, and one of those, the encoder pin number 1, is an interrupt pin. So whenever something is happening on the pin number 3 on the Arduino, and this something is basically a pulse coming from the encoder, an interrupt will be generated, and the interrupt will do something. And it will involve the encoder pin 2, which is connected to the pin number 4. And then we want to store the pin 2 value in a variable, but this value can be either 1 or 0. So we will just store it in a variable, in an integer. And then we have the PWM motor driver, which I showed you, that tiny red board. And then we have the pin 11 chosen for this. And why? Because this pin is independent from the timer, which is used to generate the timing for the millis. So then we can have maybe a bit less noise, and then we don't really interrupt with the internal timing of the Arduino, which we actually use extensively throughout this code. And then we have the PWM value. You have to be very sure that you use it as an integer, or you will convert it or cast it into integer when you use it, because the analog write function only accepts integers. I don't know how it will work with floating point or long or double numbers. I wanted to avoid these funny behaviors, so I just went for the integer. And then we have 3 pins. So one pin is the direction 1 and the other is the direction 2. These are just outputs, and whether they are high or low, they will be decided by the direction of the motor. So if you want to rotate the motor clockwise direction, you use a certain combination of these 2 pins. And then if you want to use it in counterclockwise direction, you use another kind of thing. So this will basically determine the polarity of the power fed to the DC motor. And then the standby pin is very important, because this can shut down the H bridge, which drives the motor, so it can avoid unnecessary heating and so on and so on. And then the motor direction is just a value for us or for the code. So it will be stored as a variable to see whether we go clockwise, counterclockwise. Then this is the Rotary encoder based code. So we have the CRK pin, which is also a interrupt pin. So it goes to pin number 2. And then we have DT and the switch. So they go to 7 and 8 in my example. And then we store the value of the Rotary encoder's button in a variable. Maybe I can make it 0. And what we can see here is that it can be 0 or 1. So this is read by the digital read function, and based on this, the code will decide whether we pushed or not the button. And then this will just keep track of the time, because I implemented some very simple debouncing for the button. And then we have the Rotary value. So this is a value manipulated by the encoder. So I'm not directly writing into the target position. I could do that, but I want to store the target position in this variable. And when I press the button, I pass this value to the actual target position. And then the code will know what is the target position, and it will try to move the motor there. And then the previous Rotary value is just used to detect changes in the Rotary encoder's position. So what this will actually do is that it will only update the display when there is a change in the value of the target value or the Rotary encoder's value. And I think that's quite good, because you don't need to constantly update the display, so it will not blink, for example, and it will not interrupt with the rest of the code. So that's why I did it. And then we have the target value or set point, and this is just a target position. And then we measure some values, so that can be the motor position. So this is determined by the magnetic encoder attached to the shaft of the motor. And again, similarly to the previous example here, I just want to keep track of the changes. So whether a change occurred, I will know that. And based on that, I will be able to update the display only when it is necessary. And then the most important thing here is the PID parameters. And yeah, you can neglect this. I just tried to use these values, but they were totally wrong. So we have 3 PID parameters, and I'm not going to explain them how they work and how you can tune them, because there are many much better explanations on the internet out there. And in order to really understand this, you really need to read a lot. I also needed to read a lot and study a lot about these 3 parameters and what they change and how they change. But for my motor, for this actual application, this is what I found good. As you could see, the motor was not really oscillating and not really searching for the target position. It went there almost immediately. And then this is the control signal, which is fed to the analog write at the end of the code. But this is the sort of process variable. And then we have some PID related values. And these are the parameters, which I'm not going to explain one by one because it is written in the comments here and there. So these are used to calculate the actual parameters used in the final equation, which will actually give you the value of the control signal. Then this is just a bit set of variables for the Rotary encoder. So you can see that we have something with the CRK pin and something with the DT pin. These parameters or variables are used to determine the rotation direction of the shaft of the Rotary encoder. And then we arrived to the setup part. I was using the serial communication, so of course I initialized it. But then I used the I2C because of the display, so wire has to be started up. And then we go to the pins. So we have the motor encoder related pins, and that is encoder pin 1 and 2. And as I showed it earlier, we use the encoder pin 1 as an interrupt pin. So we have to attach the interrupt to it. And this function will be called whenever there is an interrupt condition is fulfilled, which is this. So when there is a rising edge pulse coming in, then this function will be called. And then we have the standby pin. It does not really need an explanation. It's an output pin which can be turned high or low. And then the rotary encoder. This is very, very standard stuff. So we have the 3 pins. Here I used the pull-up, the internal pull-up resistors, as you can see it in this part of the code. And as I said, the CRK pin is also an interrupt pin. So we assign this thing to it. So this rotary CRK pin will be used as the interrupt pin, and it will call this function, the rotary encoder function, and it will look for changes. So whenever there is a change in the pin state, the interrupt function will be fired. And here I immediately save the current states of the pins, so whether they are 0 or 1. Then this is again some copy-paste part just to initialize the display. And then I just set up a simple font, clean the display, and then I set the font to double size, and then I just print some welcome message, and then I reset the font size to ×1. I wait a little bit, I start the timer for the display. So then from this we will wait for a certain time to search for or ask for the next update of the display. And then I clean the display. I place the permanent items on the display. I will show you this function very soon. And then I refresh the display based on the positions of the encoder. So this is done in the setup. And then in the loop we have 5 functions, but now I'm just using 4 because the 5th one is just used for debugging for me. So first, what the microcontroller does is that it calculates the PID parameters based on the target value, and then it does something with the motor, which means that it will drive it with the previously calculated parameters. And then we also check the rotary button if we pushed it or not, and we also refresh the display if we have to. So then this is the check encoder function, which is fired by the magnetic encoder on the motor's shaft. And what happens here is that whenever this starts, we check the other pin's value, and based on the value, so based on the position of the other poles, we do something with the motor position variable. So in my system, it looks like this. So if the pin 2 value is 1, we know that we go in the clockwise direction, so we increase the value of the position by 1. And then if we went in the other direction, so this was 0, then we decrease the position value. And that's how it works. Then drive motor is this function. So this happens after we calculated the PWM parameters. So it is better to first look at this function, the calculate PID. So what happens in the calculate PID is the following. So first we check the current time in microseconds, because we just run the loop without any delays. So it can happen that we enter the same function, this, within just a few hundred microseconds. So I thought that it's maybe better to just check it with the micros instead of millis. So immediately we can calculate the time. And since we use microseconds, we have to divide it by 1 million, because 10 to the minus 6 second is 1 microsecond. So here we just do a very simple calculation. Current time minus the previous time is the delta time, so the time difference. And this will be needed for the derivative term, for example. So then we save the time here. It's all fine. So this is just the time-related part of the code. And then we go deeper. And first, we calculate the error value, which is, as I said, the difference between the current position of the motor and the target position or set point. So then this error value will determine the rest of the parameters. So we have the E dot, and this is terms which we use in physics, for example. So the dot above a certain parameter, for example, x dot, that means that the position's time derivative, so dx divided by dt. And here it's dE divided by dt, which is the derivative of the E, the error. So what we have here is that we have the dE, so error value minus the previous error, divided by dt, so delta time. And with this, we are done with the derivative term. This was pretty simple. And then we go to the integral term. So then the integral term, which is just having the continuous function divided by, let's say, bins, and these bins are summed up, which will at the end give us the area under the continuous function. And that's what we do here. So you can see that this is sort of a running sum. So in each iteration, we take the previous already accumulated integral value, and then we add this term to it. So the error value plus the time difference. And just to make it more visually appealing, then I put this in parentheses. So what happens is that we have the previously accumulated sum, plus we add the most recent sum. And the error value is basically the height of the bin, and the delta time is basically the width of this bin that we going to create. And this is just a small rectangle under the area of the function. And then we are done with the integral, so we can calculate the rest. The proportional term was not mentioned yet, but it is here. So I did not put it in a separate variable because it is just too easy to calculate it. So we have just a proportional term or proportional constant times the error value. So this is the proportional term. And then we have the derivative term constant times the derivative term itself. And then we have the integral term constant and multiplied by the error integral. So this term, and this term are these guys here. So when all this is finished, we just save the current value of the error value as the previous error. So the next time when the code comes here, it will see that the previous error is from the previous, let's say, moment. And then this will be the most recent moment error value. And then we have these print values. I'm not using it. This is the one function which is commented right here. But what I did here was I was just printing the motor's position on the serial terminal, but I'm not using it. So now we have the control signal, so we can return to this function here, the drive motor function. And what we do here is first we check the control signal's sign. If it's less than 0, it's a negative number, so obviously the motor direction has to be -1, so negative. And then if it's positive, so larger than 0, then the motor direction is +1. And if it's exactly 0, it can happen because that means that basically we arrived at the set point, then the motor direction is 0. And why I have these 3 different conditions separately you will see it will make sense very soon. So then we calculate the PWM value, and the control signal is a floating point number. So we take the FABS, which is the absolute value calculation for floating point numbers, but then we immediately cast it into integer because the PWM value will be passed to the analog write function, and that needs an integer number. And then I have some cheating here. So what we do is that if the control signal tries to be higher than 255, then we just cap it. We say that whatever the value it is, it can be 10,000, it will be still just 255, because this is an 8-bit PWM capable microcontroller. So we cannot really feed larger than 255 to the function, because it will not make any sense. But here I have to notice that if you have a better PWM controller, which can generate, let's say, 12-bit numbers, then you can use obviously a higher number here, 4095. But for 8-bit controller, this is what we use. And then here, I wrote the explanation here, but I just quickly tell it that I have noticed that this specific motor under a certain PWM value just simply stops. The current which is fed to it, it's not enough to keep the motor moving. So what I do here is that if the error value is not 0, so we are still going towards the target, and the PWM value drops under 30, we don't let it to drop under 30, so we keep it at 30, so the motor will move and will actually approach and reach the target. So that's what we do. And then I previously mentioned that we will do something with these 3 separate motor direction values. So that is basically what we feed to the motor driver. So for the motor driver to determine the position or to determine the direction of the rotation, it will need 2 pins. So we will have to set 2 pins, high and low, in order to tell which direction the motor will rotate. And if the direction is -1, then we want to move in counterclockwise. So we have to set the direction pin 1 to low and the direction pin 2 to high. And then we have to feed the opposite of this. If we want to move in the opposite direction, it makes sense. But otherwise, if the value is 0, then we pull both pins to low, and we also pull the standby pin to low, so no power goes to the coil of the motor, and we also set the PWM value to 0. This is a bit of cheating. It might be a bit of a dirty practice. I'm quite sure that there are much more knowledgeable people out there who know much more better solution. So please comment if you know a better solution. But what I do here is that if we set the motor direction to 0, that also suggests that we reached the set point. And that also suggests that we don't want the motor to move anywhere. But I have noticed that sometimes the PWM value, especially if I don't use this kind of function, can get stuck at, let's say, 1 or 2 or 3 or something like this. And you can still hear a small whining from the motor. And that means that there is some power, even if just a little, but there is some power running through the coils, which you might want to avoid, especially if you have a very tiny motor, because that can sort of burn it, even a tiny power. If for example, the PWM value oscillates a little bit or something, you can heat up the motor quite nicely and you can burn it. So this might not be the best practice, but this is what I found the safest practice, let's say. So now what we did so far, we determined the direction, then we determined the control signal, we set the direction, and now with this analog write, we also set the actual value. So we send out this value to the motor driver. So we will send out through the PWM pin, and we will send out this value. And optionally, if you want, you can print these 4 variables. So after we drive the motor, we can see how the error value, the PWM value, the target position, and the motor position changes. So this is how it works. And finally, we have just these, let's say, printing things. So the permanent items on the display will be the text-based things. So we put the target text to the first line, and I have to tell you that these arguments are defined in a funny way. So if you want to move along the x-axis, so horizontally, the unit is in pixels, and if you want to move on the vertical axis, you want to move in between the lines, then in fact this argument is defined in lines. So therefore, when we want to print the position, we just move to the 3rd line, number 2, because we start the counting from 0. 0, 1, 2, and that is 3. So we print the position. And why I do this, as I said, is just to save some resources, because we don't want to clear this from the display and reprint it again, or just reprint it again without clearing. So we just print it once and we will never need to touch it. And what we really need to do is we need to refresh the display and the parts which are not, let's say, constant. So these are the dynamic, let's say, values. And what I do here is like 2 steps. First of all, I just check every 100 milliseconds. This was wrong. I check it every 100 milliseconds if one of the values were changed. If not, I don't do anything. If, for example, the rotary value changed, which means that these 2 variables are not equal anymore, then I just move to the 2nd line, erase the previous value, move back to the, let's say, start of the line, and then I print the rotary value there, and that's all. I refresh the value, and I refresh the timer. And then I check the other line if I have to update it. So let's say I have to, because these are not equal anymore. So I jump to the 4th line, erase the previous data basically, and then I set the cursor back to the beginning of the line, and then I print the motor position. And since the motor position here is a floating point number, I have to limit the number of printed digits. I set it to 0, so you will see this number as an integer. And that's all. And we don't do anything if this condition is not fulfilled, so we just skip this. Then we have the button and the rotary encoder part, so that's fairly simple. If this is fired because we rotated the rotary encoder, we read the pin, and then what we do is that we check if it was the same as previously or not, and then we also do a comparison between the DT and the CLK pins, and based on their difference we will do this. And why I do this is because I know that I want to rotate at least 515 rotations in order to do 1 full turn on the geared shaft. But I know that if I want to reach, for example, 11 times this, which is the number of pulses which I will receive from the encoder when 1 full turn is done on the geared shaft, then I will have to rotate the encoder a lot if I just use 1 increment. So here I use, let's say, 1/11 of the total number of pulses which is necessary to reach 1 full turn on the geared shaft. I hope this was clear enough, but this is how I do it. Otherwise, you can just use something like this if you want to have like 1 increment, but of course I want 515 increment. So basically this is how it works. And then finally what we have here is we check the rotary button. So every time when we iterate in the loop, we read the state of the switch. And then if the state of the switch is 0, based on this circuit which I use, it can be 1, depending on how you wire your button, pull up or pull down way. So I check if it was 0, then we can enter this part, and we see that if 1 second elapsed since the previous button press, then we pass the rotary value to the target position. So this will actually trigger the calculation of the PID parameter. And then we also pull the standby pin to high. So we enable the motor driver and we refresh the time. And when we refresh the time here, that also means that this function, whatever you do, will not be fired for the next 1 second. And this will work or act as a sort of a debounce mechanism, but with a software way. So this is how it works. And then once this position is passed, or the rotary value is passed to the target position, then we are basically done. So as you can see, this is not big of a deal. I think the magic or the science behind a good PID controlling is basically finding the good values. And there is so much good resources on the internet. You will find much better resources than my explanations. So just Google it, simply tuning PID or how to set up PID and so on and so on. And you will learn it. And also you can learn it by doing, because of course each system has a different response. And this is how PID tuning basically works. You have your system, you have the response, you have to tune these 3 parameters in order to have the proper response that you want. And in our case, in this video, the response is reaching the target position with a reasonable precision. So yeah, it's relatively or fairly simple. But of course, this takes some time to find these variables and really get the system done and really get it working. So basically this was my video, and this is sort of an introductory part for the PID controlling from my side, because I want to have PID control for other things that I have lined up. So follow my channel, please, if you are interested in these kind of projects, because there will be a lot of projects which involve DC motors, encoders, and PID controlling in general. So hopefully you will find those helpful and interesting. Don't forget to visit my website, curiousscientist.tech, because all the resources, this source code, the schematics, and all other stuff can be found there. And also you will find a lot of other things there. For example, if you want to buy the same parts I used in this video, you can also find those circuits and so on and so on. So I hope you learned something. I hope this video was useful to you, and see you in the next video.